So how is everybody doing?
All right. How about you?
How's your
All right.
so far? Bruce, you're not on.
I've been being certainly kept up lately by certain conditions, I guess.
What did you say? You've been what?
Being kept up lately by certain conditions, but
Have you been working on your stuff?
yes, just my sleep keeps getting interrupted by this, so it's just I'm a little dreary.
Jacob, how is your stuff?
Going okay.
Did you guys get the message from Chicago AMS about the meeting on Thursday?
No.
Nope.
Jacob, did you?
Nope.
Have you signed up for the Chicago AMS? Maybe you haven't. Okay, so what I'm going to do
I probably haven't.
is, hold on, let me look at Gmail. Those of you watching on recording, this is probably weird. So let me get this to you. You know what I'm gonna do, Jacob? I'm gonna forward this to you.
Me too, Paul.
Well, I'll show you what I'm gonna, hold on.
Oh, okay.
Forward to Jacob. Jacob, because if you can post this,
Sure.
you'll see it. But for you guys, oops, I will show you something here. And where is my, oh, here we go. So this is this is something from NIU, and Aaron Zeeb is the president of the NIU AMS, and he talked to his advisor from the REU project, which is Research Experience for Undergraduates. So this guy, David Peterson from the Naval Research Laboratory, is going to be talking about the fire cumulonimbus. So it's this Thursday at 4 p.m. And then this is the link to the Zoom. So just so you know, if you're interested in doing that, it's available. You know, to be honest with you, I've sort of like not done anything for the Chicago AMS because I'm on Zoom so much. I just don't have the motivation to do this. Our Chicago AMS was enough tough stuff to work on to try to get live people coming in, but now to set up a Zoom meeting to do more of this. But since this was available, I'm like, great. So maybe I'll start this up in the wintertime when things are a little bit better, but it's going to be beautiful weather for the next couple of weeks. So there you go. But you can't make it, Jim, on Thursday?
I got a FEMA class.
Oh, bummer. I don't know if anyone's going to record that, but it'd be worth doing it. So if you're interested, go ahead and do that. And Jacob, if you wouldn't mind just posting that on our COD AMS, even though we really aren't much of an organization without students. I think we're on the same thing. So the reason I was late this morning is Jim had a problem the other day, and I was like, oh, I know I have done this before. And I had to go get my notebook because the stuff that I had written this stuff down, I was still in my office. So I couldn't just go in. I mean, we're talking 15 seconds. If I had just gone in the door, grabbed the notebook and walked out, 15 seconds. And I had to set up an appointment to go there. So I walked to COD this morning, and it was actually an hour round trip. And when I got home, I was quite warm and sweaty, so I needed a shower, which is why I was late. Okay, seriously, do you have your smell camera on?
No, thank goodness.
So how are your problems? So Jim's problem, if you want to take a look at what it is, and And it was kind of fun. We were going back and forth a little bit, and I spent a lot of time working through the problem. And Jim's problem, if you want to go to page 110, this is a problem number 362. This is one of the ones that is assigned for you. So this problem deals with entropy, which we haven't gotten into, so I don't want to go into the whole solution of it yet. But if you take a look, when you look at a problem, what you want to think about is what are the key words that are coming up here? Okay, so we're talking about entropy, so you need to go, okay, this is an entropy change. You should find some delta S someplace in there. And then it says an ideal diatomic gas. Now, why would they tell you it's diatomic without telling you what it is? That's going to be the question that you ask. And then it gives you some pressure changes, pressure changes and temperature changes. So, Jim, you started doing that whole, whatever you did with that little gamma, which gamma is important. So we're going to be using that in another problem. But I don't think you need to use gamma in here.
Yeah, I know.
So
I did it. I did it two different ways. My first method that I showed you, I called my stubborn method, and then there's the practical method.
Well, it was interesting. I mean, you know, one of the great things is when you work through stuff that you don't know and you keep working because, damn it, you're stubborn and I'm going to get it. That is probably the best thing anyone can do. So that one is just going to be dealing with the ratio of CP to CV to R of 7 to 5 to 2. So I want to show you something here. This is kind of a dumb thing. Let me get over here, explode you guys up. I wish this would automatically do this for me. Okay, so here, takes a while to get this screen opened over there. I'm going to pull up Epic Pen to show you something about that relationship, because we have talked about that relationship. So I'm going to start here, put on the black screen. And
Epic Pen.
The Epic Pen. CP to CV to R for a diatomic. Right, and this is not necessarily something you would have to memorize, but it's 7 to 5 to 2. And I started thinking, so CP, what you'd want to do is this is 2CP equals 7R. Because if CP is 7 times bigger than the 2 of the R, then this would be equivalent. So you have to know how to set up the algebraic relationship. In other words, R is going to be 2/7 CP. Now we know for air, CP is 1,004 joules per Kelvin per kilogram. So this is 2,004, this is going to be 287, which is really nice. But that's just the way that you deal with those relationships. So when you're looking through the entropy section, you're going to see a delta S equation, and it's going to have a CP, and it's going to have an R in it. And you don't know what any of them are, but you can't have that many variables. So you need to put it in terms of one variable, because you can eventually go to R star, and then you can actually solve the problem. Okay, so that's why they tell you the number of moles, because you don't have to deal with what the masses are. You just know you have a number of moles, and you know what R star is, and so you can get this relationship in there. So I just wanted to give you that as a little hint. I know what you did, Jim, was really cool, and I'm glad you worked through that. I just didn't know why you were at that point, but it did stimulate me to doing a whole bunch of problems, and you had a nice little solution. It was a trick, right? You minus one, and then you just have, you think of the exponents, and it's weird stuff. So,
Can I ask a question about the question that was actually on the Unit 2 worksheets?
Yeah, absolutely.
It was the one, I think, after VT, where you had your explanation of VT.
Okay, so let me do this. Let's go to our Blackboard page. While I'm going there, Mike asked me to say he was struggling through some stuff. So I want to give you a chance maybe on Thursday to ask me some stuff about review of things that we've gone through that you may not fully understand.
Well, this will be one of them.
And oops, spring. Oh, I don't want spring. And we can go through that on Thursday, do some review of things we've already done. Now, Mike also said something about maybe getting together in person, so we could do Alfie's. I think he was talking about maybe Friday, so we could do Friday noon. And I think it's supposed to be a really amazingly great week, isn't it? Have you guys seen the weather?
No, it's supposed to get nice.
Except for the hurricane.
Except for the hurt. Well,
Yeah.
that doesn't affect us. But look at the temperatures this week. Every day, the temperatures are forecast to be at least in the upper 60s to 70.
Which is about normal.
That's nice.
This is going to be true Indian summer. So I love this. It's going to be great. So if we did do something on Friday, if you wanted to do lunch, we could certainly go to Alfie's. They've got outdoor seating. We could sit there and have lunch. Are you guys fairly close to school?
Yes.
Moderately
Less.
so.
So I will let Mike ask you when he joins us again on Thursday. We can set that up if we're interested in that. I've got something to do Friday night, but lunch would be really fun to do that. We could just talk about we could do an outdoor meeting for some weather stuff. So here's your class notes. And here's the Unit 2 worksheet. And we'll go ahead and open that. And where are you looking now? After the virtual temperature? Is this where it's at?
Yeah. The given.
Where at? Did I miss it?
Right, where you say given E equals 6 millibars, T equal 298, that's the question?
Oh, yeah.
Okay. The first thing I did was calculate the virtual temperature, then density at 1020. And I think the next step is to calculate the mean virtual temperature.
No.
Okay.
You want to do, this is a problem that deals with scale height. H.
Okay.
So you know what you're going to be basically doing is you have equations of the scale height. So you know that the pressure at 500 millibars is 5.3. So you know Z at two different places. And you're basically going to calculate the scale height based on this temperature.
Okay.
Okay. Then use that scale height to realize how density is also decreasing with the scale height. And since you know what the density is at the surface, you would say, well, what's the density at 3.5 kilometers? So you're assuming an exponential drop in density, just like there is a pressure. So if you think of this as being a scale height problem, you'll get the right answer.
Okay. Second one, formula 328, which is calculating the mean virtual temperature.
Yes.
Integrating the numerator. It's an integration by parts because TV is dependent on P.
Right. So basically,
And then you would the actual integration would be where's the definition of TV? 316.
right.
So the integration of that would be just integrating the denominator with respect to P. So 1 over P goes to just integrating that.
Yeah. So
Okay.
all you're saying is that you can create, and they do that by looking at figure 3.2. Okay. So if you look at 3.2, you're able to look at these little areas. So you plot out the temperature, And then you find in the layer that you're looking at, you're going to find a middle point so that those little areas in blue are equal to each other, or what you would assume is approximately equal to each other. But the point being is, in order to do that, it must be on a logarithmic pressure.
Right. Okay.
And as long as you're doing it logarithmic, if you did it linearly, then that would not work. But because you're doing it that way, that is the method of determining. So I can look at any sounding, look at the layer that I'm interested in, and then calculate what approximately the mean virtual temperature is going to be.
Okay.
By just kind of plotting that out.
Okay.
So yeah, so that's basically what you're doing. Is these problems are just doing little manipulations, so that it makes you deal with hydrostatic, or no, not hydrostatic, but the virtual temperature correction and the little bit of the H, the scale height, hypsometric stuff. Okay. All of this stuff we've gone through pretty well. We've done through enthalpy. So these are all like notes. We did this in class, which was kind of nice. Here's Poisson's equation. Here's some of the stuff on latent heats, and here's where the problems are. Now, notice that we stopped the notes at this section. So these are your main problems. Have you done them yet? This is not something, these problems don't take 5 minutes. Some of them take half an hour, 45 minutes to really work through. And I can't help you if you're not doing them, first of all. So you need to get into doing them and attempting them and struggling through them. If there's one thing that students learning a high-level science struggle with, it's doing problems like these. But you've got to do them. And there's only one way to do that, and that's to get dirty, work through it, struggle through it, ask questions. Okay? So how are you doing on those then? Nick, how are you doing on it?
I really haven't attempted them yet. I feel like I maybe did one of the problems, but I don't remember where.
There's so many. These are things you cannot wait to do. You need to do now. Okay, so I won't yell at you like I used to make my classes cry, but that's usually after the test. But you need to do this now. Now I know Jim's done it, because if he was asking me about 362, I'm assuming have you done at least attempted these other problems, Jim?
I've got them all done.
You got them all done. So wow, see, that's intrinsic motivation.
No, it's being old and grumpy.
But it's kind of fun when you get it right. Don't you feel good about
it? The thing that scares me is that all the algebra tricks are starting to come back.
Yeah. Well, something that I've always give lectures on is that people who struggle through calculus are because they're weak in trig.
Yeah.
Who struggle in trig are because they're weak in algebra. And the reality is most of you are weak in algebra. You forget how to do stuff. And the only way to get better at it, like anything else, is just to do it until you figure it out. Those rules will come back to you when you struggle through it. Learning, level 3 learning, where you fail and then you succeed. And that's what's really great, is when you do fail and then you do it again and then you finally figure it out. There's so much. I wish people could feel that more often, because that's where you start going, oh, I like science, because you feel powerful when you actually figure stuff out.
But in their defense, Paul, the algebra that you and I got taught is different than what these kids got taught.
I'm not going to disagree with you.
The rigor that we got pales in compare what they got.
That's a shame. It really is. And technology is, it's funny. Technology, in my opinion, is antithetical to being successful in math. So the other day I was trying to do, even online, I was trying to do it on my computer with my pen, and I was trying to solve these problems. And the only way that I could actually do them, which is hard to see, but I had to take a piece of paper and start writing it out and coming up with methods to be neat and to work it through. So James, that's where it needs to be. This is where you learn to be neat, because you can't do it without being organized or neat. So you got to work. So keep that in mind. Okay, turn to page 88, 89, please. And we're going to look at the top of page 89, okay? So I'm going to go ahead and put this back up there just because I want to go ahead and write it here for you. And we have this. Now, the left-hand side. So I show you this, and I want you to think about this on a test. I want you to think about this in life. You see an equation in a book, and you say, well, what the hell is this? Okay, so James, what is this?
It looks like an equation to talk about how height changes with time, I want to say.
Okay, but what's this mean?
Second prime?
Second order.
It's the
Second
second order or the second derivative.
Second derivative.
If
That's
I
it.
said this, right? That's the first derivative. And then you say, that's a question, how does z change with respect to t? But I don't think that's necessarily a good statement to say, how does height change? What do you mean height is changing? Nick, what do you say? How would you answer that question? What does it mean that height's changing?
I guess maybe, what's the word? It's on the tip of my tongue, but I can't think of it.
How about you, Bruce?
How fast is the parcel rising?
Okay, so if that's the case, what are you telling me then, Bruce? What are you giving me?
Vertical speed.
Okay, it's a vertical speed. So one way that you could look at this is you could sit there and go, well, this is a vertical velocity, W, right? We know, and you should know that. And then you said something interesting, Bruce. You said, how fast is the parcel rising? Okay, and why would I say parcel is actually a good way to think about this thing? What is this called?
First order differential vertical velocity.
You know, but okay, let me do this. This as opposed to this. Why this versus this? What is this called?
First order differential.
No.
Derivative.
Well, what kind of derivative? Jacob, what kind of derivative?
It's a good question.
As opposed to this. What are these called?
That's
One on
partial.
the right is a partial.
Okay, this is called a partial derivative. And this is called a what?
Full.
No. Bruce, what did you say?
Full was my guess.
No. We did this earlier this semester. James?
Total. Oh.
So find your notes and go find out what total derivative is. Like, what did I say about what a total derivative is? Because this was like, the first, I don't know, week, 2 weeks of class. What do you guys have? You must have it. Go ahead.
It refers to, now how do I pronounce it? Lagrangian, the
Right?
total.
This is Lagrangian. So
Yeah.
first of all, there is a word that you need to know how to use. You've got to be able to use it. Well, that's Lagrangian. And then what else did we say about what Lagrangian was?
The way the whole atmosphere moves as a whole.
No, not the whole atmosphere. And guys, I know that you have it in your notes. Well, I hope you do, gosh. I hope you do. Because I gave you this stuff. This is where, I wish Allison were here, because she's really good at remembering these important facts.
Oh,
What does it say, Jim?
I got it. Lagrangian total derivative, Eulerian at a point.
Okay, so this is Eulerian, right? Eulerian, which is at a point. That's what you should have for this. And it's what we call a local, right? What's happening at a point? It is a material derivative. It is right there at the time. It is right where it is. It's at a point. This is a station observation.
Would instantaneous be?
Instantaneous. Well, they're all instantaneous, but this is.
Yeah.
So in other words, if I said to you, I'm at a point, I'm looking at what the temperature's doing. So I'm at DuPage Airport, and the temperature's gone up in an hour. That temperature change is dz or dt partial. But total derivative, which is Lagrangian, you should have something in there. You should have that should be in your notes. Total derivative follows the parcel. In other words, imagine that I have a parcel that I just create in the air, which is just a collection of air. And inside the parcel, I have a thermometer. Right? That's inside the parcel. And that thermometer flies around with the parcel as it goes through the atmosphere. Or maybe it's the wind speed or a barometer or whatever it is. You have like a station ob inside the parcel. However it moves, you're looking at the changes in the temperature, the changes in the pressure, the changes in the wind speed, whatever. All of that is a total derivative, Lagrangian, following a parcel. So Bruce, when I said, what is this? And you said, well, how fast is the parcel rising? That would be correct. Because it's a total derivative following a parcel. Now, it's a shame because when they teach you calc, see, this is where I have a problem. Like if I were in charge of the world, the way that I would do it is I would teach you a whole bunch of things about what calculus is. For the whole first semester of calc would be all doing big important things. Then the more advanced courses would be, all right, here's the exceptions, here's how I actually solve problems. But I want you to get used to the language of mathematics. Because that's what I'm teaching you is the language. Right? When I take you to a foreign country, I don't teach you how to conjugate verbs. I teach you how to ask questions to talk to people. Where is the bathroom? What kind of food do you have? Give me some wine. Important terms. And then you start learning the vocabulary because as a foreigner, you're going to struggle through speaking correctly. And then you start going and you appreciate why you have to say something different because you need to communicate. Now, I want to go back to my original question. If I gave you this, which in my classes.
That's a question.
And what's the question? See, and this, James, this is important. What is this question?
Oh, x changes in relation to t.
And what's x?
X could be any variable.
No. X is
Displacement.
the what? What'd you say?
Displacement?
No, dx is the displacement. What is
Oh,
x?
just X. Oh, location.
X is a location.
Wow.
Marks the spot. The change in your location is a distance. That is the displacement. So dx is the displacement, but x is the location. So what's z if I'm thinking x, y, z?
Altitude.
It's an altitude. It's a location about, or it's a location on a vertical axis. So this really is saying, best saying is, well, how does my location vertically change over time? That's what this is. And then you'd say, well, wait a second, that's a vertical velocity. Because my location, I am at some z, and if I change my location, I am at a delta, I am some z plus a delta z. I'm someplace different. That is a change in the location vertically. So if this is a velocity, James, then what is this when I put a second derivative? What do you call the change in some velocity with respect to time?
Acceleration.
That is an acceleration, isn't it?
Acceleration.
A vertical acceleration. But so this here in the pink box is the same way. Those two are equivalent.
Oh, okay. Yeah.
I mean, I could have written this.
All right.
Because they're the exact same thing. This is just a first order derivative. This is a second order derivative with height. But this W is dz dt. So you're taking the derivative of the derivative. Because the derivative is nothing more than change. So you're saying the change in the vertical location is a velocity. The change in the velocity is the what? It's an acceleration. So now I look at top of page 89 and I say the left-hand side is an acceleration. Well, what's Newton's second law? Isn't it just F equals ma?
Mm-hmm.
But the way that they have it here is A equals F over m. But do they have F over m? What do they have? F over what? Rho. But what's rho?
Density.
Which is defined as? Capital V.
Oh, mass over volume.
Right? So if I flip it, I have the acceleration. But what am I saying about the volume? What's the way that I usually talk about it? I say this is a unit volume. And the word unity means you are all one. So you're just saying unit, meaning whatever the volume is, it's 1 meter cubed. So that I'm talking about the acceleration of a unit volume. And what do we call a unit volume in our nomenclature? It's just a what? What do we call a volume? This is an easy question, guys. What do we call a volume in meteorology?
Parcel?
A parcel. Isn't a parcel just a collection of air? It's a volume.
Mm-hmm.
So this is the acceleration of a parcel. Now notice that they go, well, wait a second. This is the density of the perturbation. Remember, we said that whatever's inside this box, the density inside, is prime. The density here is the density of the air outside of the parcel. So what is the force? Well, we know that the force is the difference in the densities, because what do we call the difference in densities? What do we call difference in densities?
Mass.
No,
Oh.
there's a name for it. Hey guys, if this parcel is warmer than the air outside of it, we say it's what?
Buoyant.
Right. So the difference in densities is what we call buoyancy.
Oh.
But that's just the force. But buoyancy truly isn't a force. What do I need to multiply it by?
Gravity.
But we know that it's supposed to be over rho prime. And therefore, the acceleration is this. It's the difference in the density over the parcel's density times gravity. And that is, this is what we would call, well, what we call it is, and here's where I have a problem. It's the buoyancy force. But is it really the buoyancy force? What is it really? The buoyancy acceleration. It's the acceleration due to the force that we attribute to buoyancy.
What letter is that in front of the equation?
A.
Okay, that is an A. I thought it was a Q for a second there.
Is that better?
There we go.
Now, look at the next, underneath that equation on top of page 89, it says the pressure of the air parcel is the same as that of the ambient air, since they're at the same height in the atmosphere. So, do you agree that in both intro classes, 1110 and 1115, I say the parcel. What's the first thing? What's true about the parcel? The parcel is equal to the pressure. Pressure inside is equal to the pressure outside. When is the pressure inside equal to the pressure outside?
In ambient air.
No, when?
Oh.
Always.
Always. Right? I mean, these are things that at the introductory level, we bash into your head. It's always equal. I wouldn't bash it into your head if majors didn't need to know that for some time in the future. If you just take that course as a gen ed and you forget that, well, whatever. But if you're a major, you better remember that. Well, if the pressures are equal, can't I just use the ideal gas law? P equals rho RT, and then I can rewrite that as rho equals pressure over RT. And then I put that in there and I factor out stuff, and I'm going to let you do that because what did I say earlier today? You need to practice your algebra. So your job is to go figure this out, and then you're going to get to the next equation. Okay, so I'm going to erase all this. Questions before I do?
Where are you on page 49? Page 89.
89.
I'm right before the black box on the left side. So I am
just before equation 373.
Yeah. So what I'm getting to is this. So all I did was I took pressure, I took the density out, substituted in the ideal gas law, factored out the R and the P, which are always the same. Because one of them would be P prime, one of them would be P, but we know that P is equal to P prime if the pressure inside the parcel is equal to the pressure outside the parcel. So in my parlance, my way of displaying things, I would say the pressure inside is the pressure, or the pressure outside is equal to the pressure inside. Their way of saying that is P is equal to P prime. Those two things mean the same thing. And again, it's about understanding what is being written. Now, that's not where they end up with 373.73. So what do I have to do? What can I multiply with that will always be the same?
1.
And what does 1 look like?
T over T, or T prime over T prime.
Right? Beautiful. So let's try that. Multiply through in each one of those, and we get what? T, because 1 over there, minus T over T prime in the numerator, all over T over T prime. Now I want to multiply by 1 over T prime. No, sorry.
There's actually a simplification before you do that.
I can multiply T prime over T prime, right? Which is going to be T prime minus T all over T.
Before you start, Paul, you could take the denominator, the 1 over T prime, and bring it up to the numerator and multiply it through.
Yeah, this is one of those things where just practice some algebra and you go, oh, okay, yeah, that makes sense. Now, it says, first of all, Bruce, you see that's 3.73, okay? Then now look at the paragraph. It says, strictly speaking, what should we have been using? Virtual temperature. However, the virtual temperature correction is usually neglected except in certain calculations reading the boundary layer. Why? Because the boundary layer is where you've got the preponderance of your moisture. When you go higher in the atmosphere, your temperatures get colder, your actual amount of water vapor is less, and the difference between temperature and the virtual temperature is less than a degree.
So it'd be the direct one-to-one replacement?
Yeah, you could, because, right, what did we use? We use P equals rho RT, and what we should have been using was P equals rho RD TV.
TV. Now
the
for the
T and the RD would go away anyway, so it doesn't matter.
Right. And in the T prime, that would be TV prime?
Mm-hmm.
Okay.
Which should make sense because we're talking about buoyancy.
Right.
Changes the density, vapor content. So technically, and if I'm using a model, I better be using the virtual temperature correction. Okay, so now let's look at exercise 3.12. Now this is actually a very, very simple problem when you think about it, what's physically going on. So the air partial in 3.12, which is just over there in A. So you agree that the partial would exist on the little red line. And what do you call that red line in figure 3.12A?
Dry adiabat.
That's what's another name for a dry adiabat. You remember? I mean, dry adiabat's fine, but what else?
Right.
No? What's another name for a dry adiabat? Jakob? That was you, Jacob. What's the name for dry adiabat?
What? What now?
What's another name for a dry adiabat?
It's a good question.
Isentrope.
What?
Isentrope.
Right? Isentrope. Because theta relates to entropy, which we'll see. So. Okay, so then, so the partial is living on that line. It starts at some place, Z naught, it's at the equilibrium level. So obviously that's the point O. And it goes to a new level. And then the partial is released, and you go, oh, it moves, right? We know that. So it says let Z equals Z naught be the equilibrium level of the air partial, and Z prime is some other displacement, or as the book says, displacement of the air partial from its equilibrium level. Blah, 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 blah. Okay, then it says, what is T prime? Now look at what T prime is over here in this thing. They're saying that T prime is equal to what? Whatever the original temperature was, minus
the lapse rate, the dry lapse rate, times Z prime.
Now, why is it Z prime? See, this is the weird thing, and this is where math is just annoying. What I'm really saying is that the parcel started out someplace. It started out at some Z, and this is the way I teach. I lift it to here. What is it now? It's at some Z. Is it the same?
No.
Z? If it's not the same, it's
Different?
okay, right? If it's, this is simple English. If it's not the same, it's different. Well, how different is it? It's delta Z.
Delta Z.
The reason that they get away with this, it's the same reason, and it drives me up a flipping wall, is what do you understand the difference in this is that you have, it's ZA minus ZB.
Right.
But what are they saying ZB is?
It's 0.
So they're saying that equals ZA. So in other words, they're saying the height at a point is actually what the change is. And I think that's confusing in life. Students don't get that. It's delta Z.
Yeah.
So in my world, I would have said, instead of Z prime, I would have said delta Z.
Yeah.
How far did I lift it? And if I know it's cooling at 9.8 degrees Celsius per kilometer, I know that the new temperature is there.
Is it Z prime or is that Leibniz notation for DZ?
Well, this, because it's prime, is saying it's of the parcel. Because the environment is cooling at the dry adiabatic lapse rate. That's parcel. This is what they're saying that T0 equals T prime 0. So what we're saying is that the parcel temperature and the environment temperature start at the same place. They're calling it the equilibrium level, which is annoying. It's just the starting temperature, whatever I started the parcel at. Remember, what is the parcel? It's a collection of air. It's a collection of air. And so I started at a temperature, and it's the same as the air, outside air.
Say it's a collection of unit airs would be correct?
Yeah.
Okay.
Yeah, it's a unit volume of air.
Yeah.
And so what they're saying is then the difference in temperature between the parcel and the environment, that's what this is, right? Look at the screen. The difference in temperature between the parcel and the environment is going to be equal to what? The difference between the parcel's rate of cooling and the environment's rate of cooling times, and I'm going to use delta Z. It's a
Is that a minus in front of the lapse rate for dry?
I was just pointing to it and it wrote. So it's the difference in the dry adiabatic lapse rate. Now, why the minus sign? Well, let's think about this for a second. Parcel is warmer than the environment. What will the left-hand side be? Parcel is warmer than the environment. What will the left-hand side of the equation be?
Positive.
Therefore, the right-hand side. But if the parcel is warmer, then the environment must be cooling slower than the parcel. I mean, the environment's cooling faster than the parcel. Instability is a race against cold between the parcel and the environment. So that means this gamma of the environment is more than the dry adiabatic lapse rate, which if you look at that figure, well, I'm actually looking at more like figure B. I'm just saying if. So that means you have to put a negative sign there because the lapse rate's the rate of cooling, and you have to throw the negative sign because we know that lapse rates are defined as a negative temperature change. Think it through. It's really not as complex as I'm making it out to be. Then it says substituting the last expression. Okay, so what I end up getting for that difference in the temperature on 373 is that I get the second derivative. And again, notice that this is of the parcel. Now they put the prime in there. Did they have the prime in there before? No, but
No.
you get the idea, right? You're talking of the parcel. T's in the bottom, but now the top becomes the difference in the lapse rates. And what they're going to do, and this is the weird thing, this is just what somebody has done. They're going to call this, well, let me do it this way. They're going to call this thing n squared. That's all they're doing is they're calling it n squared. So they get this equation. And I'll put the prime in there. And okay, guys, once again, why the prime?
Of the parcel.
Of the parcel. And here I say delta z, but whatever. Z prime, because it's minus 0, is where they're starting at the equilibrium level. So if that is n squared, then understanding that n is equal to the square root of this. Well, that's called the Brunt-Väisälä frequency.
I don't suppose we can get that spelled.
Well, look at page 89. It's right there. Right after equation 375. I'm not giving you something that the book doesn't have.
Oh, there it is. Okay. I thought it was going to be bolded. I was looking for something that didn't exist.
Well, it would make sense. But that's called the Brunt-Väisälä. It's those umlautens over the A's make, I think it's a, what?
Umlaut.
Umlaut?
Yeah.
What language?
This is umlaut.
German, though. Is that Norwegian?
Nine.
Finnish.
Deutsch. Well, there's a number of languages that use it. German.
Okay, well, I think Väisälä was Norwegian. I don't know. Oh, wait, it's a Finnish. Vilo Väisälä, a Finnish meteorologist.
It's always in the footnotes.
10 p.m. on Tuesday.
And then Sir David Brunt. He was an English meteorologist, yes. Hello, my name is David Brunt. Hello. I'm Vilo Väisälä. I don't know what a Finnish accent would be. So.
Oh, there's the weekly.
Okay. And what did he good? He was really good at making instruments. Have you ever heard of Väisälä as a...
There's an instrument named that.
Yeah, they have, 10 o'clock. I hear the sirens.
Yep.
Anyway, now, what we're saying is that we have this equation, 3.74. Now, so I want you to write in your notes or whatever it is that this equation is a second order differential equation. And then they say the following. If it's stably stratified, that means the dry adiabatic lapse rate is greater than the environmental lapse rate. Do you agree that's a stable environment? That is statically stable. We've talked about those terms. That means the answer or the truth about n is it's going to be real. Because imagine that n were in an unstable environment. Then you'd be taking the square root of a negative number, which you can't do, which would make it imaginary. But this next thing in here, guys, which says z prime, or delta z really, is equal to a cosine of nt plus b sine of nt. Okay, this is way more than I'm going to get into. But when you solve second order differential equations in a form that looks like this, the solution is a series of sines and cosines.
And physically, that's a wave.
It's a wave, right?
Yeah.
There is a wave. So you might sit there and go, well, where the hell did this come from? And the answer is, when you take differential equations, this is what you learn how to do, how to assume an answer.
Well, that's one possible, so that's one way to solve it.
One way to solve it. So I'm not going to go into that. All I'm saying is that I tend to get this. Now, making use of the conditions at the point of maximum displacement at time equals t0, it follows that z prime at some time t is the cosine.
Is this being recorded?
Yes.
Okay.
Okay.
Definitely going to be looking back at this.
Well, look, James, what you need to know is that, okay, so here, I'll show you what you need to know, James. What is this thing over here?
That's the Brunt-Väisälä equation.
Well, no, it's not the Brunt-Väisälä equation. That's the Brunt-Väisälä frequency. It's a what?
Second order differential.
Second order differential.
Right? And so I want to solve, because what I'm trying to do is this, right? I'm trying to figure out, well, what is the partial going to do when I move it? Now, you know it's stable. What's it going to do? It's going to come back. Here. In order to say, well, where is it going to be at a given point in time? What's it going to be doing? What's the acceleration? If I know the acceleration, I know how its velocity is changing. If I know how its velocity is changing, I should know where it is. Right?
Yes.
In order to solve this, that's the answer. This is the answer to this equation.
Oh, that's the solution.
The solution. The
Okay.
solution to this equation. You don't need to know how to solve it. That is not for me to teach you in here. That is what you do in differential equations. Nick, have you taken your DiffyQ already?
Yeah, this looks familiar. I just don't remember how it was done, but I know I remember doing stuff like this.
Well, of course not, because you took differential equations, you got through it, and then you forgot most everything. But this, if you go back into it, you would find this is in here. So what I want to do is show you this so that for the rest of you, if you take differential equations in the future, that's what you're going to see. So all I'm saying, James, is that this is the solution to this equation.
All right, and that's cosine n lowercase t and then b sine n capital T.
Yes. And look what it says here. And I'm gonna write it up here. Excuse the messiness of the misplacement of it.
I wasn't fond of my DiffyQ teacher, okay, Paul?
Oh, was it
Is anybody?
or was it in Wisconsin?
It was in Wisconsin.
No.
I think I've got my notes for it still, though.
I've definitely had my fair share of bad math teachers in the
There it
past.
is.
Every one of my middle school math teachers was pretty bad.
Okay.
The T on the end there is a subscript.
No, I'm sorry.
I didn't think so.
It's a little t.
Oh yeah, here it is.
What does little t stand for?
Time.
Time. So I want you guys to look at this equation up here, okay? What is this equation up here saying? Read it to me. Let's go with Jacob. Go ahead, read that out loud to me.
I'm trying to think of what it's. Z prime of time of some time equals z.
But what's z prime?
Some altitude
Of?
of a parcel.
Okay, so in other words, the left side is the altitude of a parcel, or the height of a parcel at some time is equal to what?
The height of the parcel at 0. So
right,
times cosine of n times time.
So if I know what time I'm trying to figure out, then I take the cosine of that times n. Now what's n?
That's the BV frequency.
It's the Brunt-Väisälä frequency.
Okay.
So, and you're like, okay, well, what's the Brunt-Väisälä frequency? Well, it's just the ratio of gravity to temperature times the difference in the lapse rates. Now, that's how you would say this side of the equation. So yes, James, go back, refresh this, go through this. But here, I want to show you something that this is the exact same thing about. Imagine that I've got a ceiling. And hanging from that ceiling is a spring. And hanging from that spring is a weight. And do you agree that if I pull that spring, that weight down, and I let go of it, what is the spring going to do?
Harmonically oscillate.
It's going to, I'm going to move it down, and then it's going to come up, and it's going to go down, and it's going to come up, and it's going to oscillate. Well, isn't that what a wave is? This wave is a graph of my vertical location versus time. So I could use that same concept here to show you what is the position at some time t is going to be the position that I am at 0 times the cosine of some function that would go into this equation. But what kind of function would go into this equation? What's going to tell me how high up and down the spring goes?
The amplitude.
Well, I can pull it really far down, but what's the wave going to do? Is it going to sit there and go up and down forever? Isn't it going to start to...
It's eventually going to dampen.
Right? You're going to dampen the wave. You're actually going to be moving up this... Oops. You're going to be moving up like this.
It's eventually going to go to equilibrium and stop.
Right? It'll go to equilibrium. Well, what would a parcel do if you took it up to the EL? Isn't it going to go up? I mean, you'll push it past, and then it comes back down, and it's going to go up, and it's going to go down, and it's going to oscillate. In a stable environment, it will oscillate about the equilibrium level. That's exactly what it does. So the function in here would relate to how strong the spring is. Do you agree that a really strong spring will quickly bring it back to equilibrium?
Mm-hmm.
That's because there's resistance in the spring. Well, what happens in a very strongly stabilized environment, the amplitude of that wave will be a lot smaller, won't it? And if it's colder, So let's go back to this. Let's go back to what the Brunt-Väisälä frequency is. It's a frequency. It's how up and down it goes. Right? Do you agree that's what n is? What makes n bigger?
A smaller t.
A smaller t, so when it's, simple terms, when it's
Colder.
right? Or what else makes this bigger?
The difference between the lapse rates is larger.
Which makes it more,
Adiabatic.
no,
Oh,
when you
colder.
make it bigger, right? Isn't the difference between the dry adiabatic lapse rate and the environmental lapse rate when it's positive, meaning it's stable, the greater the stability, the bigger this difference is, n becomes a bigger number. The Brunt-Väisälä frequency affects static stability, it says. The higher the frequency, the greater the ambient stability. That's what this is. That's what this means. Bruce,
So
what,
if gamma D is bigger than gamma, we've got more static stability.
instability is a race to get cold. We want the environment to win. Who's winning this race?
D. Gamma D.
The parcel, right? The parcel's winning the race. So if the parcel's winning the race, the atmosphere is stable. The slower the environment cools, the greater this difference, the more stable it becomes. Now, look at the next thing. It says, air parcels undergo buoyancy oscillations in association with gravity waves, a widespread phenomenon in planetary atmospheres, as illustrated in 3.14. So we look over there and we look at 3.14, and don't we see those waves all the time? If I see those waves, what do I absolutely know must be true?
Say that again.
If, like, look at page 90. Is everybody on page 90? In the satellite picture, I see those wave clouds. If I see those waves, what is absolutely going to have to be true?
You've got stable air underneath.
Correct. It is stable air underneath because it's oscillating. Now, look over here, guys. Imagine that I had a parcel and I lifted the parcel and the parcel was buoyant. Let's say, I couldn't solve for this because this is an unreal number. Well, is this parcel going to oscillate? What will it do once I move it up? It's unstable, so it will continue to move up. It doesn't come back.
Right.
It doesn't oscillate. It just accelerates up. So if I have a wave like this, air is moving up and down, and all of a sudden the air reaches the LFC, it doesn't oscillate anymore. It accelerates upward, and I get a thunderstorm. So why do I get clouds like that? What's happening is I have to move air up. So I get mountains that are going to cause the air to go up, and then there's going to be an oscillation. It's a buoyancy oscillation known as the Brunt-Väisälä frequency.
Do you always see those with terrain underneath? Do you see maybe the question should be, do you see those over the Great Plains?
Well, what do you think would cause it? What has to happen? Like here, let me answer this question. What has to happen with this spring in order to get oscillation?
It's got to be pulled down.
Right, you need to vertically displace it. What else can vertically displace air? Besides mountains?
Vorticity? No.
Well, I suppose you could make it.
Well, it's not the right answer.
Yeah, I mean, it's sort of. You're not wrong, but
Cold front?
how about a front or an outflow boundary? Won't I?
What?
we call, if you have an outflow boundary, isn't that cold air pulling away from the thunderstorm going to force air to oscillate? If I get that oscillation in a flow, then I get what we call, I don't know if you ever heard of this. An undular bore. You ever heard of this?
Sounds like my last math teacher.
Nice one. That's really good. Okay, so let's take a look at this.
Would you see that cloud structure in an outflow?
Yep.
Really?
Oh yeah.
Oh, okay.
So let me go here. Here's Wikipedia. Undular bore. Look.
There it is.
An undular bore is a wave disturbance of the Earth's atmosphere and can be seen through unique cloud formations. They normally occur within an area of the atmosphere which is stable after an outflow boundary or cold front moves through, because what's an outflow boundary or cold front doing? It is
forcing
air. It's a vertical displacement. And then if there's a stable atmosphere, you get wave patterns that are going to go up and down.
So for a cold front, you would see those clouds behind the front.
Yes.
Okay.
Yeah, here's the leading edge.
Right.
On the leading edge, if the air that it's running into is unstable, I might be able to lift that air to the LFC, and what would I generate?
Clouds.
Storms.
Well, yeah, clouds and thunderstorms. If I go to the LCL, I get clouds. If I go to the LFC, I'm going to do this. So up here's the clouds, and they're transverse waves. In other words, you see the cloud structures, and the wind is blowing perpendicular to it. It's a transverse wave.
Wow, you can see them on the radar too.
And you can see it on the radar. So if you ever see this, you're like, oh, undular bore.
You get stable air.
Yep. But because they do that, you can go a long way. Now, we're going to get into hydraulics with a hydraulic jump and this Freud number. And we're going to get into that. So and I have to show you videos from the 1960s because it's the best thing ever. It's one of my favorite videos. It's called Waves and Fluids. And I wish somebody could redo it in 21st century technologies, but it sucks. So you get these gravity waves. And all that. So let's see time-lapse video. Let's see if we can find one. Well, here, let's see. There's the gravity wave coming through. It's pretty cool.
You can't see it as well as you can see it from the overhead. You can't see the striations.
Right. But you get this little thing of cloudiness.
Yeah, now you can see them.
Okay, what I really want to see is, gosh, where can it be? Walker, Ashley. And then, because you have an undular bore, now you have a new type of cloud. This has actually just been the official new one. It's called undulatus asperatus. It is what we would, now, here's a couple of things. In this texture, Walker Ashley sometimes calls this a whale's mouth. It is what I would call boiling. And I said underneath the shelf cloud, we get this boiling texture. Well, underneath the shelf cloud, do you agree it's cold air with warm air on top? That's stable or unstable? Cold air down below, warmer air on top. That's stable. So you get these undulations in it, and that's called undulatus asperatus.
How?
So here.
Oh, wow.
Like Walker is the best. When it comes to his time lapses, you see the wave going through.
Holy cow.
Isn't that amazing? And that's all a gravity wave. It's just, I mean, it's so cool. It's just amazing stuff. And because you've got dynamics propagation of the wave, you can get many different waves.
You'd have to watch it over time, because if you look at it quickly, you could interpret it as mamatus.
Right, and it's not mamatus, because this texture is what I call, this is what I would call boiling texture, right?
But seeing it over time is easy, but just taking a snapshot, it's hard. Just one look, it's hard to tell.
Does mamatus make sense to you? Because the air is underneath the anvil, and the anvil forms at the equilibrium level. So the air coming out of the anvil goes up and down, and that's
Up and down.
mamatus. Why you have certain stuff in there is pretty amazing. So let's see what else we've got for his. Here's another one. I don't know if that's as good as the one that we just saw, but
That's harder to see.
yeah, that's not quite as good.
You can kind of see the striations.
Yeah, and the flow is a lot more. The flow is a lot more complex, because it's not just perfect transverse flow. There's also shear probably in the environment.
Is altocumulus another word for asperatus?
No, well, altocumulus, you might know. Altocumulus is definitely an altos form cumulus cloud. So I think they say altocumulus asperatus. The technical name for that now is undulatus. So undulatus asperatus. Let's look at this. Or asperatus, I guess it's formerly known as undulatus asperatus. First popularized and proposed as a type of cloud in 2009 by Gavin Predor-Pinney, and it became added as a supplementary feature in 2017. So it's kind of cool. There's people who do stuff like this.
Cloud Appreciation Society.
There you go. Let's go to undulatus clouds. Let's see what that is. Altostratus undulatus. Here's the ones that you're seeing on page 90, Bruce.
Yeah.
Here's the altocumulus, where you see the remnants just up high, though.
That's bizarre looking.
And again, when you see this, which way is the air blowing?
Perpendicular to the wave.
Right, it's a transverse cloud. So it's blowing across the wave this way. I don't know which way, probably this way. Now,
doing like ripples in the cloud. So pretty.
And you can see this, you will see this a lot, and you'll see these waves propagate out from outflow. So, when a cold front goes through, sometimes you'll see it coming out across the oceans that are with the cold air and lofting up the stuff. The warm, unstable air is being pushed up. Now, exercise 3.13. A layer of unsaturated air flows over mountainous terrain. And then it says, for what value of the wind speed will the period of the orographic terrain force match the period of a buoyancy oscillation? So now they're saying, I'm going to look at this Greek letter tau says L over U. Okay, so what this is, and I think this is crap in terms of the book. Do you remember the other day we talked about, what's the word I'm looking for? Okay. Why am I just having a mind freeze? I'm pulling a James on you guys. What do you call it when you assign when you look at equations and you assign a order of magnitude to it? We're talking about something called scaling equations.
Oh, yeah.
Okay. Well, capital L is the length scale. Capital U is the velocity scale. That's what those mean. So I'm going length over speed. And I'm saying that is what we're kind of defining as this Greek letter tau. And that doesn't really matter that much. But so that's, in other words, what is L? It says the spacing between the ridges, between the peaks of the wave. And how fast must the air be moving? And it says, I want to make that equivalent to 2 pi over n. Because that's what it's asking. What value of the wind speed will match the terrain-induced forcing for a buoyancy oscillation? And then they just throw all those numbers in there, and they say 20 meters per second. That's 40 knots. So the solution of that is pretty straightforward when you understand what the hell they're trying to do. They're just saying, if this happens, what does that mean? Okay, so it says underneath the blue box on page 90, take a look at this. Layers of air with negative lapse rates are called inversions. A lid, blah, 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 blah. A partial, well, that's not even going to do anything. But what happens is, depending on the stability, you have certain wind speeds that match it. That's why you don't get them all the time, because you don't always see them. So when do you start seeing some cool stuff? Well, here's something for you to do. So I'm going to go up here, and I'm going to look at Kelvin Helmholtz wave. And look what we got with these things. Have you ever seen these type of wave clouds?
No.
That's cool looking.
Well, hold on, I want to duplicate this. How do I duplicate?
Right click on the tab.
Oh, right click on the tab, that's right. Okay, so let me go back for a second and then go to images.
They look like waves you would see on the body of water.
Look at this. That's cool.
Whoa.
Right? So whenever you see that, what you're talking about is a statically stable. In fact, it's got to be a certain value of stability and a certain value of shear. That's what's going to result in this. So let's take a look at what it says here. Typically occurs where there is velocity shear, common seen with wind blowing over the water. The instability is able to manifest itself through waves underwater, but you can also see that anywhere else. But I just want to go down here and see a couple of things and when I look at the equations for these things, what do I see in here?
CN.
N.
NU.
I
That's
see U. And I also see something called the
Richardson number.
Well, look what the Richardson number is. Buoyancy over shear. What else? Where have you seen this before?
On a SQT.
Like the bulk Richardson number.
Bulk Richardson number, cape over shear. So Richardson number is a scaling term. You also have something called the Rossby number, which is a scaling term. So I just want what I'm really looking for you to know is that you've got these different terms. Here's something called the Reynolds number, which is a ratio term. Talks about viscosity. So this is where you get into some more terms in here. So if I look at Reynolds number, and we're going to see this coming up. Look at the way the fluid goes out like smoke. it becomes, how would you describe this smoke from a candle flame? What is this? This is laminar. It becomes turbulent. It becomes turbulent at a certain Reynolds number. Oh, look at this, a vortex street around the cylinder. So all these things are so cool. I'm going to look at one more thing. I'm going to look at Rossby number, just because I want to show you things that we're going to be getting into. Rossby number, look at this. What did I say U was?
Velocity scale.
This velocity scale, right? And what did I say L was?
Length scale.
And what's F?
Frequency?
Coriolis force, or Coriolis frequency.
It's what we call the Coriolis parameter, 2 omega. So we will say FV when we go 2 omega V sine phi.
So that's another. So that describes a Rossby wave.
You get Rossby waves, you get numbers. It says a small Rossby number signifies a system strongly affected by Coriolis. If you've taken my mesoscale course, we are going to say the definition of mesoscale is based on the Rossby number. If the Coriolis force is insignificant, if this is very small compared to this
U over L would be just a constant.
like if the length scale is really big and Coriolis is there and the speeds, so like 10 knots over 1,000 miles, do you agree the Rossby number will be small? Well,
Right.
if it's small, it says it's strongly affected by the Coriolis force. In the mesoscale, the wind speeds are about as fast as a scaling of the length. 10 kilometers per second, or whatever. This number becomes bigger. I don't want to get into this here yet, but all of these things are all about scaling numbers, about looking at magnitude, Reynolds, Rossby, Richardson, when we talk about Kelvin-Helmholtz waves, when we talk about Bruns-Weisel frequency. They're all kind of in this fluid dynamics of how things work. Okay? So that's what a gravity, so ultimately this whole thing is all about what is a gravity wave. So I'm going to look at one last thing, gravity wave. And if I look at these things, simply put, generated fluid between medium when the force of gravity or buoyancy tries to restore equilibrium. Isn't that what we've just discussed today? That air is going to want to go back down. So a lot of times we're going to say a gravity wave is gravity is the restoring force. Do you agree on a spring? It's gravity that's trying to restore it to equilibrium. In a buoyancy oscillation, it's gravity is the restoring force. The Bruns-Weisel frequency has gravity in it. Wave clouds. There we go.
I've been there.
Where? Wisconsin?
Teresa, Wisconsin.
Really?
It's in Dodge County.
That's pretty funny. By the way, oh my gosh. Here, read this out loud, would you, Nick?
Yeah. In the Earth's atmosphere, gravity waves are a mechanism that produce the transfer of momentum from the troposphere to the stratosphere and mesosphere. Gravity waves are generated in the troposphere by frontal systems or by airflow outflow over mountains. At first, waves propagate through the atmosphere without appreciable change in mean velocity. But as the waves reach more rarefied or thin air at higher altitudes, their amplitude increases and nonlinear effects cause the waves to break, transferring the momentum to the mean flow. This transfer of momentum is responsible for the forcing of many large-scale dynamic features of the atmosphere. For example, the momentum transfer is partially responsible for the driving of the quasi-biennial oscillation.
Quasi-biennial, which means every other year.
Quasi-biennial.
About every 2 years.
Quasi-biennial oscillation, and in the mesosphere, it is thought to be the major driving force of the semi-annual oscillation. Thus, this process plays a key role in the dynamics of the middle atmosphere.
Okay, so I go to quasi-biennial oscillation. Have you ever heard of the QBO?
No.
Between easterlies and westerlies in the tropical stratosphere with a mean of 28 to 29 months. Downward motion of the easterlies is usually more irregular than that of the westerlies. The amplitude of the easterly phase is about twice as long as that of the westerly phase. Okay, so let me ask you this. When's the last time you thought about why the weather this year is different than the weather last year and said, well, it must be parts, what phase is the QBO in? And the answer is you never have. The answer is I never have. But there are people who deal with this stuff.
So
again,
the QBO is sort of how people can think about how weather changes from year to year?
Yeah. As in
Does
the
it
case
link
for
up
many
with
of
El
the
Nino?
stratospheric circulations, Richard Lindzen, James Holton. Holton is the book on dynamics. Richard Lindzen's the big, sort of more skeptic in global warming from MIT. If you've ever done that, you'd see his name.
How does it link up with El Nino?
I have no idea. To be honest with you, I don't even know this. Research has been investigating a possible relationship between ENSO and the QBO. Eastward phases of the QBO often coincide with more sudden stratospheric warming. Anybody know what a sudden stratospheric warming can do? When you have a sudden stratospheric warming, that's usually about a week or 2 weeks in advance of a significant Arctic outbreak in a polar vortex. Westward phases often coincide with mild winters in the eastern U.S., strong Atlantic jet stream. I mean, look at the stuff that goes on. These are the long-scale climate dynamics. How good are we at climate dynamics? Terrible. But I just wanted to show you how all of these things play a role. Now, as it turns out, what we just talked about is dealing with static stability. So, and it does deal with things that we're going to be doing when we get to the next unit, which is dynamics. We still have to finish this unit. So right now, we're on the second law of thermodynamics, page 93. And I know it's almost time to be done, but let's just look at this ahead. So I think we've done everything pretty well up to this point. So what do we have to do? Well, we need to deal with the second law of thermodynamics and the Carnot engine. And so this has got some amazing stuff. And it's only 3 pages. So I want you to do that. And then there's stuff on entropy and the Clausius-Clapeyron equation. So I want you to study this up for Thursday.
Can you mention what pages in particular again?
So
Just to make sure I got it down here.
sure, it's 93 to the end of the chapter. But in the class notes folder, there's two things in there. There's the Mechanical Universe, episode 46 and 47. And you don't have to do this. I would try to do 46 and then maybe try to do 47. Maybe watch that a little bit because those are good to watch. And then there's also a worksheet, make sure you have that. It's called Carnot Engine Reading, which is, well, I'll explain it to you on Thursday. But to me, the Carnot engine was the hardest thing. I just couldn't understand it in a way that I was happy with it until I read this article. So you may not understand the confusion I had, but I certainly did. And this is the only, I went through like 16 books. Where are you guys? I went through 16 books trying to find out better explanation of the Carnot cycle. And I'll tell you what I had as a problem. And all of the books, all of the physics books have the same thing, and it never answered my problem. And then this one did. And then I understood. So we're going to work on that for Thursday, okay? Carnot cycle. Today, would you think today was kind of cool?
Yeah, definitely. It's always nice to see how these things relate into the other, like the actual world events, you know?
Yeah, this is kind of cool. Different new things in the atmosphere. So we'll let Mike we'll talk about whether we're going to do Friday for lunch, but maybe that would be a cool thing to do. Anyway, guys, have a wonderful week. And I'll see Bruce. I'll see you in 15 minutes, and I'll see the rest of you guys later.
See you on
All right.
Thursday.
See you Thursday. Bye.